at the top of the hour to go over number 1A and B. It's worth 5 points. I think some of you are overthinking this. So let's talk about this. I tried to give you all the pieces parts you need to put all this together, but so in number 1, we're going to look at this substitution. So x is e to the t. Oops, cat knocked over the microphone. So x is e to the t, so that t is the natural log of x. So hopefully you remember from algebra, these are equivalent statements. You want to show that dy dx is 1 over x dy dt. So we're converting from taking a derivative with respect to x to take a derivative with respect to t. And we can just use the chain rule. Y is a function of x, but we can use t as an intermediate variable. So dy dx, which would be this rate of change, is dy dt times dt dx. And so if you look at this, there's your dy dt, which we're trying to get to. And then for dt dx, you know that t is natural log of x. So dt dx, that just means take the derivative with respect to x. Okay, so that's where that piece comes from. But what this is really saying is that if you're trying to take the derivative of something with respect to x, whatever that thing is, if you're taking a d dx, the way you do it is you take 1 over x times the derivative of that thing with respect to t. Now, if you go off into engineering and or some, depending on what you go into, like especially partial differential equations get used a lot, this sort of differential operator thing shows up when you're trying to convert between, say, rectangular coordinates and cylindrical coordinates, or rectangular coordinates and spherical coordinates. In other words, you've got this differential equation described in a generic form, and you want to put it into one of these different coordinate systems because you're working on a sphere, so you want to use spherical coordinates. Okay, so the derivative of something with respect to x is 1 over x times the derivative of that thing with respect to t. So that's what comes into play down here. All right. So if you want to take the second derivative of y with respect to x, that's the derivative with respect to x of dy dx. So this dy dx we know is 1 over x dy dt. So now at this point, I'm going to have to use what rule? So I'm taking the derivative of a product of two functions. So we'd have to use the product rule. So derivative of the first, so d dx 1 over x times the second plus the first times the derivative of the second. So the derivative with respect to x of dy dt. And so this is where that first property comes in, because I'm taking the derivative of something with respect to x. That's 1 over x times the derivative of that something with respect to t. That's where this part is going to come from. You follow? So don't overthink it. But I think some of you just are kind of going too deep or not. But it's a 5-pointer for a reason. You just have to write stuff down and then invoke the rule. So hopefully that'll make sense. And then what you do is you stuff all that into here. And remember, once you stuff this into here, now the y double prime here is a d squared y dx squared. The y prime is a dy dx. The goal is to take this diff eq and use what you learned in number 1 to get everything, d squared y dt squared and dy dt. and then you should get a constant coefficient equation where you can use y equals e to the mt. So your initial solution to this, you're going to have y be, some collection of exponentials with t. And then to get back to x, you're going to use the substitution t is natural log of x, and then use your exponential properties. Okay. So I think that's the one giving most people trouble. This seems people seem to be doing okay with that. And then don't lose sleep over this. We can talk about this. I'm just trying to get you to think about what's going on here with that. Okay, so hopefully that helps you out. All right, so you got your take home 6 and test 6. That's due tomorrow. And then you'll get take home 7 and test 7. That'll be due next Wednesday. And then we have spring break. And so because of that, you're just going to have a take home 8 is just going to be a 50-pointer. All right. Remember this week that the take home is 30 points. The test is only 20. But over the break, I don't want you having to stress about coming back and taking a test after break. So you just have a big 50-point take home for that. All right. So that's what's coming up. Alrighty. So we're looking to finish undetermined coefficients today. So once again, here's the kind of diffie q's we're looking at. They look like this. A2 y double prime plus A1 y prime plus A naught y equals f of x. So the highest derivative here is the second derivative, which makes them second order. The coefficients of y and its derivatives are all constant, so it's a constant coefficient, second order. And this f of x may or may not be 0, so it's non-homogeneous. Okay. So what was our first step to solving these things? Well, not quite yet, Ryan. But we're going to put that into what equation? Not this one, but what? We're going to go after the what solution first. Yeah, the YC. So the YC is the complementary solution. So we're going to take the diffie q and we're going to solve the associated homogeneous equation. All right. And here's where we're going to use the y equal e to the mx to get our solution to this. And once again, this is what we did in section 5.2. And then in part 2, we're going to use f of x to guess yp. All right. Now the f of x needs to be built up of functions like polynomials, exponentials, and sines and cosines. In other words, they need to be built up of functions whose derivatives end up being back in the same family. So you take a derivative of a polynomial, you get a polynomial. You take derivatives of exponentials, you get exponentials. You take derivatives of sines and cosines, you get sines and cosines. Because we're looking at a linear combination of the derivatives. So all you're doing is taking the function and its derivatives and you're adding and subtracting them to get the f of x. So if the f of x is built up of those pieces parts, we're going to guess the yp, and then we're going to solve for those, the titular undetermined coefficients, right? We'll find those. Then to get the general solution, we take yc plus yp, and then the last step, which we'll do one of these today, we're going to impose initial conditions if you have them. So the initial conditions help us figure out the C1 and C2, but we need the particular solution in there as well to make sure we're getting the right C1s and C2s. So you need the whole solution before you impose the initial conditions. Right? So if you've been tuning in or watching these videos, this is how we've been starting all these, because you got to hear stuff at least like 7 times, apparently. So I'm trying to remember which one we left off. I think we did this one. This was the last one we did yesterday. This looks familiar. So we did that one last time. So I think we're down to this one today. And once again, I'm not going to go through the plug in the YPN. We're just going to make sure we get the right start. And then you can determine whichever bookkeeping method you want. Let's take a look at this equation. We've got y double prime minus y prime minus 6y equals 18x squared plus 6x minus 50 cosine x. So on the left-hand side, the highest derivative is the second. So it's second order. The coefficients of y and its derivatives are constants. So it's a constant coefficient equation. And this is equal to something that's not 0. So this is a non-homogeneous constant coefficient equation where the f of x is built up of polynomials and cosines. All right. So this is a great candidate for what we've been working on the past few days. So first step, we're going to find that yc. So what would be the differential equation we would be solving here to figure out the yc? Yep. Yeah, I'll write the diffie q down and then we'll get the algebra one in there. So that's there it is. Now in m's we get this. And the first question we always ask ourselves is, does this factor nicely? Otherwise we can always hit it with the quadratic formula. It factors nicely. Very good. What do I get from my m's? 3 and negative 2. So that means for our complementary solution, we're going to have a c1 e to the minus 2x plus a c2 e to the 3x. Any questions on getting the complementary solution? Once again, this is the stuff we did in 5.2. All right, next step. We want to know what the yp is. So we're going to look at the f of x. So the f of x is 18x squared plus 6x minus 50 cosine x. Right? So let's guess the yp. So once again, you see we've got a polynomial part and we've got a cosine part. For the polynomial part, since we're plugging this into a constant coefficient equation, when you plug a polynomial into a constant coefficient equation, the highest power of the polynomial is going to be at the level of y, right? Y is going to have the highest degree because as I start taking derivatives of polynomials, those powers are going to decrease. So I see I've got myself a quadratic here. So in the yp, the highest power of x I'm going to need is a quadratic, so I'm going to need something ax squared. But as I take derivatives of ax squared, I'm going to get x's and I'm going to get constants. So even though here you only see x squared and x's, I need to have constants represented because as I take derivatives, I'm going to be getting those. You follow? Derivatives of linears will give you constants, and then the second derivatives of quadratics will give you constants. So we need to represent those. And now I look at this term here, I've got a cosine in there. But as I take derivatives of cosine, who else is going to show up? Sines. Okay. So that's going to handle this part. Are there any questions on this, getting to this part? And now we're going to do a quick double check. Is anything duplicated in the complementary piece? So our complementary piece, c1 e to the minus 2x plus c2 e to the 3x. Is there any duplication between the yp and the yc? Nope. So that means we're good to go. So then we're just going to plug in yp, and then we can equate coefficients. And we talked last time about why that's completely legal to do that, because all of these basic functions here, x squared, x, constants, cosine, and sine, all of these are linearly independent from each other. And then you get the general solution, yc plus yp. And so once again, I'll leave that to you to do it. We've done a few examples, different ways to try to keep track of things. It's just bookkeeping. Remember, when you turn stuff in, keep it neat and organized so I can follow what you're doing. I think we've also talked about checking these on Desmos enough times that if you're going to check them on Desmos, I think you know how to do them by now. Okay. Next example. Y double prime plus 6y prime plus 9y equals 72x e to the 3x. Once again, the highest derivative you see, y double prime, makes it second order. The coefficients of y and its derivatives are all constant. So it's a constant coefficient, second order equation. It's equal to some function f of x, which isn't 0. So it's a non-homogeneous second order constant coefficient equation. Okay. So step 1, find the yc. So that's the complementary solution. It's the solution to the homogeneous equation. So what do we get out of this? Does that factor nicely? Yep. One may say it factors a little too nicely, because the only real 0 we get here is what? -3. We get -3 with a multiplicity of 2 because it comes out twice. Okay, well, we know how to handle that. C1 e to the minus 3x plus, and then this came out of reduction of order last week. We're going to revisit reduction of order tomorrow to see it work in general. But what ended up happening? We did a little reduction of order on this. We ended up just slapping on an x. There we go. Okay. That's our YC. Next step, we want to guess the YP. So I look at what the f of x is. So the f of x is 72x e to the 3x. So think about the yp. Once again, we have to imagine what kinds of pieces, parts are going to get produced. So once again, the yp itself is going to be part of the differential equation. So we're going to have to represent that as some a x e to the 3x. But as we take derivatives of ax e to the 3x, what else are we going to get? Yeah, terms that just have e to the 3x in it, right? So I'm going to have to represent those b e to the 3x. So once again, you have to imagine plugging that function or something like that function into the diffie-q and representing all of the different linearly independent pieces parts that are going to come from that derivative. That's your yp. And now I got to check with the yc. Now the yc in this case was a c1 e to the minus 3x plus a c2x e to the minus 3x Do we have duplication here or not, folks? Well, actually, no. Yeah, it's close. I mean, the next example we do. But it's close. But these are positive 3s. These are negative 3s. And remember, if the exponentials are different, they're linearly independent. Okay? So we got no duplication. So we're good to go. Now you just stuff this in. And then your final answer here, there's no initial conditions, yc plus yp. Okay. So once again, I expect you to, at some point, plug this in and get things to work out. All right. You check your answer on Desmos or check your answer here to see what you get. It's not necessary to factor out the e to the 3x, just like we didn't factor out the e to the minus 3x here. I think I did this because this is kind of how the book, I think, presents the answers. But whatever. Okay. Now, once again, this is the classic. This is a classic Carl problem right here. Here's the one we just talked about. Here's this one here. What's the only difference between these two? Yeah. The f of x has an e to the minus 3x in it. So we have the same left-hand side for the diffie-q. So the yc is going to be the same as before. And we go to guess the yp. Well, you would start with this. So you would start with ax e to the minus 3x and then think about taking derivatives, and you would get e to the minus 3x's. But now we look for duplication. And what do we see? Everything's duplicated. Once again, what does that mean? Any linear combination of e to the minus 3x and x e to the minus 3x, when substituted into the left-hand side, will produce 0. So if you took this yp and plugged it in there, everything would cancel out, and you would just be left with 0 equals 72 e to the minus 3x. That'll tell you something is wrong. Okay? So once again, how do we eliminate the duplication? We want something that's linearly independent from what I've got down there, but close enough to plug into the differential equation. So what do? I start slapping on what? X's. Now, if I multiply through by x, I'd get an ax squared here, which is no longer represented here, so that's good. But then I'd have a bx here, which is represented here. So I actually have to slap on how many x's here to get this to work. To eliminate the duplication, I'm going to need what? So if I do it once, so if I multiply by x once, let's do it this way. I still get duplication. So if at first you don't succeed, what do? Nope, there you go. Okay. So you want to multiply by enough x's so as to completely eliminate duplication. Because once again, if I had just plugged this into the left-hand side, you would have parts of this and its derivatives would survive the process, but this would completely get zeroed out. Any questions on how we got the form of the yp here? So now you stuff that in, determine your undetermined coefficients. There's your YC, and there's your YP. Okay? So once again, I hope you take the opportunity to actually work through the details on these so you can see how the stuff shakes out. All right, so we'll finish up looking at this last one here. It's an initial value problem, so we'll just remind ourselves how this works. But once again, we've got a second order differential equation, constant coefficient, non-homogeneous. We go off to the YC. What do I get for my m's here? It's plus or minus 2y. And once again, if we have pure imaginary solutions, that means we're going to get pure oscillations. What's my YC going to be? Yeah, cosines and sines. So C1 cosine of 2x plus C2 sine of 2x. So that 2 there, that the coefficient of I, that's your frequency of oscillation. Okay, good. All right, now I got to guess the YP. So I look at the f of x, and I've got a constant e to the 2x sine of 2x. But if I start taking derivatives of this, I'm also going to be picking up what? If I plug that into the dpq, yeah, e to the 2x's cosine 2x's. Okay. Now I need to look to see is there duplication. There's a cosine 2x and a sine 2x, but in the particular solution we've got these exponential factors, and so these are linearly independent functions. They're different functions than what's in the YC. You follow? Because to be part of the complementary solution, the C1 and C2 are constants. So if I stuff these in, these are not constants. You follow? So these are linearly independent pieces parts. So there's no duplication. I can just plug these in, set it equal to, plug it into the left-hand side, set it equal to the right-hand side, and get my particular solution. So any questions on the setup here of getting your complementary solution or then guessing the particular solution? Are we getting comfortable with that? Because if you don't have the right guess, then the whole thing's not going to, the thing will just be, will get messed up. All right, so you go through that particular solution. and you get the general solution, would be your yc plus your yp. The yc would be c1. We put the cosine first, didn't we? Cosine 2x plus c2 sine of 2x. And then we would have 3 e to the 2x sine 2x minus 6 e to the 2x cosine 2x. Right. So this would be this is your yc. The yc contains the constants. And then this would be your yp. So once again, I encourage you to go through the machinations, go through the bookkeeping, practice that, get something that works for you, that'll also work for me, to show me how you're getting these coefficients. This particular problem, though, is an initial value problem. All right, so we're going to write this on the next page here. Y equals c1 cosine 2x plus c2 sine 2x plus 3 e to the 2x sine 2x minus 6 e to the 2x cosine 2x. We got a couple initial conditions here to work on. We've got y at 0 is 1. Y prime at 0 is negative 4. So once again, it's an initial value problem because you're plugging in the same x value. We're looking at what's happening at x equals 0. Y at 0 being 1 gives us the y-intercept of the curve. What's the y prime at 0 be negative 4? What's that telling us about? Yeah, that gives us the slope at 0. So that's a negative 4 slope. All right, so let's plug these in. Y at 0 is 1. So when I plug in x equals 0, cosine of 0 is 1. Sine of 0 is 0. So that's going to zero out these two terms. And then e to the 0 is 1. So I get right away that c1 is 7. So this gives me that y is 7 cosine 2x plus c2 sine of 2x plus 3 e to the 2x sine 2x minus 6 e to the 2x cosine 2x. Okay. Now I need to impose the next initial condition. Y prime at 0 is negative 4. So to do that, I need to figure out y prime. So when we're taking derivatives here, don't forget about the chain rule. When I go to take the derivatives of these sine and cosine functions, what's going to be popping out? You got a factor of 2 you got to worry about. So here, the y prime, you're going to have a 2 come out. So it'd be minus 14. Sine of 2x. 2 pops out. Plus 2c2 cosine 2x. And when I go to take derivatives of these next two terms, what rule do I have to use? Yeah, product rule. And once again, if I look at when I go to take the derivatives of these exponentials, I'm also going to get a factor of what to pop out. So when I take the derivative of the first factor, 3e to the 2x, I'm going to get 3e to the 2x times 2. That'll give me 6e to the 2x sine 2x. Plus 3e to the 2x times 2 cosine 2x. So that's going to give me a 6e to the 2x cosine 2x. Over here, I'm going to have a 6e to the 2x times 2 cosine 2x. So that'd be a minus 12. And then I'm going to have a 6e to the 2x times a minus sine of 2x times 2. So minus 2 times minus 6 would be a plus 12 e to the 2x sine of 2x. And now we want to plug in 0. So once again, if I plug in 0, all the terms with signs in them will cancel out. Cosine of 0 is 1, so I get that 2c2. So you see it's important to remember that 2 comes out. 2c2 plus 6 minus 12 is negative 4. So when you look at all that, you're going to get 2c2 is what? 2, which means C2 is 1. All right. So now I go back. We had C1 cosine 2x plus C2 sine 2x plus 3e to the 2x sine 2x minus 6e to the 2x cosine 2x. We've now determined that C1 was 7, C2 is 1. So we get down to our final answer. Okay, so there's an old saying, one of the mantras I enjoy the most: the more you understand, the less you have to memorize. This is sort of the recipe sheet for undetermined coefficients. Like, here's like if f of x contains an x squared, then your yp is x squared and all the things below it. But if you understand why this is, in other words, if you have a polynomial that's going to go in for your y, the highest power of x is going to come from that y term. As you take derivatives, you're going to get all the lower powers of x are going to be in play. So you have to have that. So if you see an x to the n power, you need a generic polynomial of degree n. You need degree n and all the powers before it. If you see an e to the mx showing up, then you need to have things that look like e to the mx, because as you take derivatives of e to the mx, you're just going to get e to the mx's again. If you see an x squared e to the mx, then once again, you got that polynomial piece. As you take derivatives, you're going to get all the lower powers of x. So you need to put that in there. If you see a sine or a cosine, you got to include both, because once again, as you take derivatives of sine and cosine, you're going to get sines and cosines. If you see a polynomial times sine or cosine, then you need the generic polynomial. So you see the pattern here, folks? And if you've got terms that are duplicated, then you just have to keep multiplying by powers of x until there's no longer duplication. All right, so here's an example of about the duplication. Now you only have to put the x's on the parts that are duplicated. So if you have for example, if your initial guess to the complementary solution was this e to the 3x sine and cosine, but your complementary solution had the e to the 3x's in it, you only have to put the x's on that. That's the principle of superposition. This will be the same. So we did an example like this, I think last week. All right. So there's your homework. It's spread over 3 sections. It's kind of nice your author spreads it out like that. But once again, I would encourage you to go through and fill in all the details on the stuff from yesterday and today, because they're kind of rigged to have things to show you certain things. At the end of the day, once again, keep your work organized and neat so it's easy to follow, and find a system that works for you that's organized enough that I can follow it. Okay? All right, tomorrow we're going to go back and revisit reduction of order. We mentioned reduction of order last week. That's how we got that in section 5.2, how we knew to slap on an x if we had a repeated 0 in the auxiliary equation. So we're going to be looking at reduction of order in a more general sense and doing a couple examples of those. I anticipate Thursday will be a work day because there's going to be examples I'm going to leave for you to do, and I really want you to do those examples and ask any questions about them on Thursday. Friday we'll have our office hour for additional Q&A. And this afternoon my office hours are going to be remote only. I don't think anyone in DiffyQ, I think Daniel's come in person, but remote only today from 4 to 6. All right. So if I don't see you, have a great rest of your Tuesday, and we'll see you tomorrow.